Welcome to a confidence interval example. So this example, a study was run to estimate the proportion of California community college students who have dependent children. A random sample of 100 students was drawn. 31 students were found to have dependent children. Find the 95% confidence interval for the proportion. So the very first thing we want to do is just simply understand the problem statement. Right now, we know that this is a confidence interval for proportion because that's the only thing we've learned so far. But we will have lots of different inferential or forms of inferential statistics that we can run by the end of this semester. And so it will be important to distinguish between them and then find the key pieces of information we need to actually find the interval or run our hypothesis test. So key here, we're trying to estimate the proportion. So even if we didn't have the fact that we were looking for a 95% confidence interval for proportion, we would know that that would be what we were doing. We have a random sample. This is extremely important. We can do nothing if we do not have a random sample of 100 students. So right here, what I've done so far, we know that we are taking a confidence interval for proportion. So it's a confidence interval. And it should be based on the p-hat distribution. So we're finding a confidence interval. Based on p-hat distribution. It's proportion. We have a random sample. And not only is it random, it is drawn from the whole population. We know that our sample size is n is equal to 100. We had 31 students out of those 100 had dependent children. So here's our 31 students having dependent children. So that can give us p-hat. We have 31 out of 100, or 0.31, have dependent children. And I just realized I forgot one key piece of information to denote. It's a 95% confidence interval. We will actually have a few others that we find. So this is just pulling the relevant information from the problem, the important information, and identifying what type of problem we are running. Next, we have to justify that the study was run appropriately. So some key things that we need, basically, we need to know that our sample was drawn appropriately and we meet the conditions to have a normal distribution. So first up was the sampling method good. That's the first thing we need to check. We do have that it was random and it drew from the whole population. So random and drew from the entire population. So we meet that condition. Next up, we need to know our conditions for the normality of the p-hat distribution met. So where the conditions for normality of the p-hat distribution met. I'm going to give myself a little more room here. One moment. Now we can continue on. So what we need to check here is we need n times p and n times 1 minus p, both 10 or more. So we have a little bit of a sticking point here, and that we do not actually know p. Instead, we know p-hat. So we only know p-hat. So we use that instead. So using p-hat instead of p, we have n times p-hat is 100 times 0.31, or 31. And n times 1 minus p-hat is 100 times 1 minus 0.31, otherwise known as 69. Both of these are 10 or more. So we meet our condition. So I would usually write a sentence for this. Again, I did not give myself enough space. So our sentence would be we can find the confidence interval because the sampling technique was good. And the conditions were met. For normality of the p-hat distribution. From here, we are going to jump into understanding the sampling distribution. So we are working with the p-hat distribution. We're working with a p-hat distribution, and we need to know what we can of the shape, center, and spread. So for the shape, we just saw in step 2 that the p-hat distribution is essentially normal. So for our shape, we know that it is normal. We did this in step 2. For the center, Recall that mu sub p hat is equal to p. Well, this is precisely what we are trying to estimate. So we don't know this. This is what we are trying to estimate. This is what we wish to estimate. Then the last thing we want is the spread. So the spread, we'll do sigma sub p hat. And the formula we had for that was p times 1 minus p divided by n. When we do p times 1 minus p divided by n, we don't know p again. So instead, we will use p hat to approximate p. So we will do the square root of p hat times 1 minus p hat divided by n, or the square root of 0.31 times 1 minus 0.31 divided by 100. If we plug this into the calculator, inside the square root, we wind up with 0.002139. And then once we have taken the square root, we wind up with approximately 0.046. So we have our shape, we have our spread. The center is what we are trying to find or estimate. At this point, we have enough information to find our confidence interval. So the very first thing we need to do is find our point estimate. This is the base of our confidence interval, or the sort of the point we're taking our wiggle room from. So this is the base of our confidence interval. And it is just our sample statistic. So we have p hat was equal to 0.31. Now for our margin of error, recall from the previous video that 95% of samples were within 2 standard deviations of the center. So recall 95% of samples were within 2 copies of sigma sub p hat of the center p. It actually turns out that we can be more precise than that. So more precisely, 95% of samples are within 1.96 copies of sigma sub p hat. So the 2 is just, it's 95 point something% are within 2 standard deviations. But if we want specifically 95%, it turns out we only need to go out 1.96 copies. Let me give myself a little more room. So we can use for our margin of error for 95% confidence, our margin of error is actually just 1.96 copies. We don't need to use 2. So the margin of error for 95% confidence we have, I'm going to call it ME, is equal to 1.96 times sigma sub p hat, or 1.96 times, in this case, 0.046. And we wind up with approximately 0.090. From here, we build our confidence interval. Recall our image. We start at our p hat, and we jump up by our margin of error and go down by our margin of error. And then this stretch is our confidence interval. So we are going to do p hat minus our margin of error is on the left. So this is the left side, is p hat minus our margin of error. So we have 0.31 minus 0.090, otherwise known as 0.22. For the right side, we are looking at p hat plus our margin of error. So 0.31 plus 0.090, otherwise known as 0.40. Again, giving myself some more room. Our confidence interval, 95% confidence interval, is P, the true population proportion, falls between 0.22 and 0.40. Or in symbol notation, we would denote this as 0.22 is less than P is less than 0.40. Finally, our job is to explain the results of the study to the general public. We have a generic statement that we use, which basically incorporates the P falling between these values, just putting it in words. What does P stand for in this problem? And the generic statement, we will start off with I am, here's our first blank, confident, or the researchers are, as another way, that blank falls between blank and a blank, and then I will explain what this means. So the first blank is our percentage. So I am 95% confident. The second blank is what it was we were trying to estimate. So we were trying to estimate the proportion of California community college students who have dependent children. Falls between precisely what we were just found. So 0.22 and 0.40. So again, this first is our confidence level. The second blank is what we were trying to estimate, or what we wish to estimate. And this is the left and right side of our confidence interval. What this means is that we are estimating, so ways the general public might understand this. So based off of the study results, uh, the proportion of California community college students who have dependent children falls between 0.22 and 0.40. Or in other words, we estimate between 22% and 40% of California community college students have dependent children. And this technique works, or the technique we used for running our study and calculating the confidence interval will yield an accurate result 95% of the time. So the technique used for selecting the sample and finding the confidence interval will yield accurate results 95% of the time. So essentially, there's a 5% chance that we picked one of those samples that is not representative of the population. And there's a 95% chance that we picked a sample that is representative enough. So when we do confidence intervals, we're never 100% sure that we are accurate in our estimation. But we can say essentially the likelihood that our technique worked. So this is confidence intervals. In the next video, I'm just going to go back through this same problem. I'm not going to resolve it. I'm just going to make a couple quick comments about some things to take note of that you might be able to use in your own problem.